So let's recap with chapter 4. Did I start that? Yeah. So we're talking about functions. As I mentioned before, the concept of a function and keeping the domain and the range of a function straight seem to be one sticking point for students. So please let's stay on top of the material in this section. So in this class, a sticking point in this class, and then in the modern algebra, math 4510, 4520. So given a set D called a domain and a set R called a range, okay, a function f from D to R, so f colon D arrow R, is an assignment of an element of the range to each element of the domain. If x is in the domain, the element of R assigned to x is written as f of x. So this is something more general than the algebraic notion of functions that you started learning in high school and dealt with in calculus and all that stuff. This is a much more general notion. Because calculus type functions are not sort of the be all end all of how functions are used. Although they are examples of what I'm talking about. So the most sort of basic type of function with a finite domain and a finite range that you can do is simply this kind of bubble diagram. And you can think of any function this way. You have domain elements and range elements and arrows from the domain to the range. Everything in the domain gets one out arrow. And things in the range can have several in arrows, one in arrow. So there's 3 in arrows, 2 in arrows, or no in arrows. So what this picture means is that the function at 1 goes to A, the function at 2 goes to A, the function at 4 goes to A, at 3 goes to C, and 5 goes to C. Couple things to notice: f of 1 is equal to f of 2, but 1 is not equal to 2. And there is no x in the domain such that f of x is equal to b. All right. There is no, in other words, that is, for all x in the domain, what? Right. No x in the domain satisfies f of x equals b. So taking the no out of the quantifier, right, that is all x in D. For all x in D, what?
f of x is not equal to b.
Yeah, exactly. Right, different ways of stating a negation. Well, so, stating making a negative statement with universal quantification. So there is no x satisfying this, means that all x don't satisfy this. So examples of functions that you've been looking at, in calculus and pre-calculus, the term function is used for algebraic expressions, with the domain being some subset of the real numbers and the range being a subset of the real numbers. So like polynomials, right? F of x equals x to the third plus x squared plus 1. So f of 0 is negative 1. F of 1 is 1. F of 2 is 11. Things that we've looked at, predicates, those are functions whose domain is something. Can be just about anything. And the range is always just the set t comma f, true comma false. So logic valued functions are what predicates are. Given a function f from D to R, and here's where the confusion starts: images and pre-images. The image of A under f is defined, so you have a function f, and A is a subset of the domain. So the image of A under f is defined as, okay, so we use f of capital A, It's the set of all f of little x such that x is in A. So sort of intuitively, you will think like this. If this is the domain, in terms of the bubble diagram here, and this is the range, then if this is the set A, then f of A is all the stuff that A gets sent to under F. Right, so here's A, there's f of A. So, for example, and then the image of f itself, right, the image of the function itself is f of the entire domain, which is often written as image, IMF. So, for example, here's a function, right? The image of f, it's the set of all f of x such that x is in D, and you'll notice that it's A, B, and C. Little d doesn't get used. If A is equal to the set 1, 3, 5, right, 1 and 3 both go to A, and 5 goes to C. So the image of 1, 3, 5 is just AC. If A is equal to 1, 2, 3, then the image of A is little a, comma, little b. All right, so examples of images. All right. Let f be a function from domain to range. And say that A is a subset of B, is a subset of the domain. So A and B are subsets of the domain. Right. Remember, we proved that A is a subset of B and B is a subset of D also means A is a subset of D. Now that we have that fact, we can just use it. Anyway, so since if A is a subset of B, prove that f of A is a subset of f of B. Okay, so how do we prove one set is a subset of another? Okay, you take an element of the one set, the smaller set, let y be an element of f of A. Show that y is an element of f of B. Okay, pay attention to how we do the proof here. So let y be an element of the image of A. By definition, y is f of x for some x in A. By the way, you can't start with, like I was saying last time, let f of x be an element of A, then let f of x be an element of f of A, then x is in A. Totally doesn't work. That's not true. That's not true. For example, here, right, f of 1, 3, 5 is little a, little c. But f of 4 is c, right? F of 4 is equal to c in this picture over here. Right? Here's 4, goes to c. But 4 is not an element of the set A over here. Okay, so subtle kind of difference there with the image. All right, so the way it goes is you let y be an image in the image of A. Therefore, there is some x in A such that y is f of x. Okay. Now, because A is a subset of B via assumption, okay, we get that x is in B. X is in A, and A is a subset of B, so x is in B. Therefore, f of x is in B. So, because y is equal to f of x, y is equal to f of b. And here I rewrote the proof more succinctly, right, using sort of a, more succinctly but incorrectly, using sort of a string of notation. So at the end, right, here we had x is in b, so now y, which is equal to f of x, is in b. Rather than saying, so now f of x is in b, so because y is f of x, we have y is equal to b. Y is an element of b. So here it's said just in one go. It doesn't matter if you're more comfortable saying something like this rather than this. Stacking symbols together can, get confusing at first. Whatever is more comfortable for you. In some of the homework, by the way, and also in the exam, I've noticed sort of misuse of notation. Notation is very important in writing mathematics. The way you use notation conveys the ideas that you're trying to say. The notation is a shorthand for the English. So, if you're using, English and, words incorrectly, you can't communicate. Same thing in math. You use the wrong symbols. If you use the symbols to mean something other than if you use symbols that mean something other than what you're talking about, then you're not communicating effectively. So like I often saw something like this, like, A intersection A union B complement, where A and B are sets. Right, and then someone did this. So by De Morgan, not someone, several people, we did like A intersection B, and then, so what's wrong with this that I'm writing here? What's wrong with what I'm writing here? Like here, I had like my mistake there. I had this symbol rather than this symbol. What's wrong with what I'm writing here if A and B are sets? What's this symbol mean?
Should it be an equal sign and not a double
It's an
multiplication?
equal sign, yeah. What does this mean? This means if and only if. That's for logical expressions, predicate or propositional logic. Doesn't work with sets. Doesn't apply. I also saw kind of like, this sort of thing. What's that? Maybe you mean implies in the logical sense, but, or this expression goes to this expression or something. It's not saying what you want to say. The point is that they're equal as sets. These are equal as sets via De Morgan's law, via distribution, and then, so on and so forth. Okay, the right notation needs to be used. It's just like using the wrong words in English. If like here I wrote this. So y is an element of f of x. Meaningless. Completely meaningless. Y is an element of f of x. Right? Y is an element of the domain. F of x is an element of a range. They're not sets. They could be sets in some way. In some weird way, it might make sense, but in general, no. It's just nonsense. Doesn't mean anything. Y cannot be an element of f of x. F of x. Oops, what happened here? Oh, touch this in my hand. There we go. Y is equal to f of x. That's what we were saying right here. So, all right. So please, be careful about that. Notation is really important, just as vocabulary is. Did anybody ever see the movie The Princess Bride? I'm sure you have. Come on. Anyone ever seen it? The Dread Pirate Roberts and Wesley and Buttercup and all that. Nobody's seen it? You're killing me. Yeah, okay. So anyway, it's like the one character, how he keeps using the word inconceivable, but he doesn't use it right. It's kind of like that. Nobody really quite understands what you're saying. All right. How about this? suppose that, so let's do let f be a function from the domain, so not let, but consider a function f from the domain to the range. And A and B subsets of the domain. Suppose, oh, wait a minute, is this the one I did for homework? Yes, that's the one I assigned for homework. Let me think. Something different. Yeah, it's fine. So let's show that. Yeah, this is about, okay. Prove that f of A intersection B is a subset of f of A intersection f of B. The image of A intersection B, okay, is a subset of the image of A intersection image of B. Okay? So how do we start a proof like that when you're trying to show subset? How does the proof start? First sentence. What's the first sentence in the proof? I'm trying to show this set is a subset of this set.
Would you assume
Let, actually.
or let the function? Would you like do the first part?
Well, we've already got this. This is already known. A and B are subsets of D.
Oh, okay.
So we just want to prove that this is a subset of this. So a subset type proof always starts out how?
Let X be an element of
Of
A
of which?
intersection B.
Yeah, F A intersection B. So actually I'm going to use a Y here. Let Y be an element of A intersection B, but X would be fine. So therefore, by definition, right? So by definition, what? Right. What is this? Let us write out what this is. The image of A intersection B. It's the set of all what? Now here's the image of A. It's the set of all f of x such that x is in A. So here the image of A intersection B is what? It's the set of
Set
what?
all f of x such that x is in A intersection B.
Exactly right. So now by definition what? There is x in A intersection B such that what? Right, so y is an element of f of A of image image of A intersect B. Y is an element of the image of A intersect B.
Such that y equals f of x.
Right, such that y is equal to f of x. All right, now because x is in A intersection B, what? X is where?
X is an element of A and an element of B.
Yeah. So So now what? If x is an element of A, f of x, so y, which is f of x, is an element of what?
F of A and F of B.
Yeah, is an element of f of A, and y, which is equal to f of x, is an element of f of B. Or you can say it the way you said it, f of A and f of B. It's fine. Right? So y is an element of what?
The image of A intersection the image of B.
Perfect. Very nice. All right. How about this? Okay. So prove that. So now show that f, the image of A intersection image of B, is not necessarily a subset of the image of A intersection B. How do you show not necessarily? Not necessarily. I mean, it might be. F of A intersection F of B could be a subset of F of A intersection B, but not always. Right? So if something is sometimes true but not always true, you say it's not necessarily true. Right? Not necessarily true. So how do we show that something is not necessarily true? We provide a horse of
Counterexample.
counterexample, the horse of a different color. Right? It's not necessarily, so it's not all horses are not necessarily brown. You show horses are not necessarily brown by showing one non-brown horse. Counterexample. Okay, so to do this, we provide a counter example. So a counterexample is a example that disproves, that shows that a universal statement is false. A universally quantified statement is false. That's a counterexample. So we need some function in some A and B such that f of A intersection f of B is not a subset of f of A intersection B. And this is actually easy to do. Now, when doing counterexamples, okay, the cheesier, the simpler the counterexample, the better. Okay, elaborate counterexamples don't, like, it's fine. I mean, it is. I mean, from a strictly, from a perspective of just, saying it's not true, it's fine. Or if there are no simple counterexamples, it's fine. But if there are simple and cheesy counterexamples, you give those first. Okay, so something like this, right? Some bubble diagram with some just real simple domain and range, and I'm gonna redo the F here. So, for example, something like this. So we'll say 1 goes to A, 2 goes to B, 3 goes to C, and 4 goes to A, 5 goes to B, and 6 goes to D. Say. Right, and let A be 1, 2, 3. So A equals 1, 2, 3. And B will be equal to 4, 5. Right? So in this case, right, A intersection B is what?
Empty.
Is the empty set. So the image of the empty set is just what? By definition. Right? The image of the empty set, it's the set of all f of x such that x is in the empty set. So that is just what?
The empty set.
Just the empty set. Right? In this case, A intersection B is the empty set, so the image of A intersection B is the empty set. However, the image of A is equal to what? What's the image of A in this function here?
Set ABC.
Yeah, little a, little b, little c. And the image of B is what?
Little a, little b.
Little a, little b. Therefore, before we get to the therefore, and so image of A intersection image of B is the set little a, little b. Therefore, in this example, right, f of A intersection f of B, image A intersect image B, is certainly not a subset of the image of A intersection B. Okay, so that's a rather disappointing property of functions, is that the image of A intersection B is a subset of the image of A intersection image of B, but not the other way around. Not the other way around. The image of A intersection the image of B is not a subset of the image of A intersection B. So this is in contrast to the fact that the image of A union B is equal to the image of A union the image of B. And you would prove that, okay, you would prove that by showing that the image of A union B is a subset of the image of A union the image of B, and the image of A union the image of B is a subset of the image of A union B. And that's one of your homework problems. That is homework problem number 2. Okay. So in homework problem number 2, you will actually prove that the image of A union image of B is equal to the image of A union B, and you prove that using, by showing that this is a subset of this, first is a subset of the second, and the second is a subset of the first. But it just doesn't behave as well with respect to with intersections. Okay, this is one of your homework problems on assignment 4. All right, so for next time, okay, consider f of A, the image of A, and the image of B, minus the image of B, and the image of A minus B. One is a subset of the other. But not necessarily the other way around. Right? So of the two statements, f of A, f of B, subset f of A minus B, and f of A minus B, prove the one that's true. And give a counterexample to the one that is not. Okay, I mean, set difference is just intersection, so, I mean, but try not to use that set difference is the same as intersection, right? I mean, this is, well, no, I guess you could, because this is like, right, the image of A intersection, the complement of the image of B. And then this is the image of A intersection B complement. So one is true, the other is not. Okay, try to prove the one that's true. Figure out which one, is true. And the one that's not, give a counterexample. Okay? So next time we'll go over that. All right. Next bit. That was images. There's a lot more to do with images. We'll do some more as we go along here. The next definition is pre-image. Again, definitions really important. You need to understand definitions, okay? Because that's everything that we're talking about. Everything starts with definitions, and then you go from there. And that's sort of one of the unfamiliar aspects of what you're learning here, is that things are defined, and then you're expected to talk about those things that are defined, shortly thereafter. Whereas in pretty much all of high school, middle school, high school, and calculus and differential equations, these types of courses that you been doing all throughout, your mathematical learning career, it's not that. They don't throw definitions at you. Sometimes they do. There's one here and there. But I mean, you have like a whole semester or a year to digest it, a couple years to digest that definition. Okay, not the case anymore. Definitions are thrown at you, you digest them right away. So anyway, so given a function, f from domain to range, and a subset of the range the preimage of A is. So it's denoted this way. Please don't say F inverse. Please don't say F inverse. This is the notation that's used, okay, but it doesn't mean inverse function. The inverse function doesn't have to exist. Right? There's a function and there's sometimes an inverse function, but in general, inverse functions just simply don't exist for general functions. They're just not there. They don't make sense. We'll talk more about that as we go on. There's only one very specific circumstance under which inverse functions exist. Preimages, however, they always exist. Preimages exist and they're very well behaved. They exist and they're well behaved. So when we're doing this, please say preimage, don't say F inverse. Not because, I don't know what your meaning is. I won't know what you mean. I will know what you mean if you say F inverse. At least I hope I'll know. But I want to make sure that you know. So don't confuse it with that. So it's the set of all x in the domain such that f of x is an element of A. It's the set of all it's the set of all x in the domain such that f of x is in A. And the definition is kind of why it's well behaved. There's sort of a universal quantification built into it. It's everything in the domain that goes into A. Whereas with images, it's not so. You just have some things in the domain and you're sending it to whatever it goes to in the range. So that's kind of an existential type quantification. These are some things in the domain that go to that stuff in the range. Preimage is here's everything in the domain. Sorry, here's everything in the domain that goes to that stuff in the range. So more on that in a moment. So that's the preimage. Example. So let's use that same example we had from before. Let's add a little something to this. Let's add an element E here. So here's domain, here's range. Actually, let me go down. A page. All right. So let's say BC. So if A is equal to little b, little c, okay, then the preimage of A is equal to what? It's all the stuff in the domain that goes to little b, little c. So what goes to little b? Which function, what's that? Yeah, go ahead.
2 and 6.
2 and 6. 2 and 6, they go to, they go to little b. What about little c?
4 and 5, it looks like.
4 and 5. All right, so if A is equal to this, then pre-image of A is that. What if it was just one element? Again, inverse functions don't exist. This expression here does not make sense. This expression here does not make sense. There is no F inverse of B. I mean, if there was an F inverse of B, what would it be? 2 or 6? What would it be? I mean, if you wanted to have an inverse function, right? So the the inverse image of B. I mean, is it 6 or is it 2? Which one takes precedent over the other? Well, neither one does. It's ambiguous. That's why they don't exist. These inverse functions. If you want to talk about the preimage of a single element, it's this. Preimage of the set containing 2. So now the preimage of the set containing, what did I do? B. Ugh. Preimage of B is, 2 and 6. All right, the preimage of the set containing B is 2 and 6. The preimage of the set containing B and C is 2, 6, 4, 5. How about this? What is the preimage of the set containing D and E? What is the preimage of the set containing D and E? Which stuff in the domain goes to little d and little e in the range?
Would it be the
Nothing.
empty set?
Nothing, empty set, right? All right. Preimage is much more well behaved than image. So let's prove that the preimage of A intersection the preimage of B is equal to the preimage of A intersection B. So whereas the image of A intersection B is not the same as the image of A intersection image of B, one is the subset of the other is not necessarily, with preimage it does work, they are actually equal. As is the union with union. So here we got the preimage of A union the preimage of B, exercise number 3, is equal to the preimage of A union B. So that you will prove. We'll on your homework. Let's do this here in this class. Okay. So prove that the preimage of A intersection preimage of B is equal to the preimage of A intersection B. So how do we show that two sets are equal?
You show that they're both subsets of each other.
Right. So first we'll show that preimage of A intersection, I'll do it the other way around. Preimage of A intersection B is a subset of the preimage of A intersection the preimage of B. Okay. Well, let X be an element of the preimage of A intersection B. So now I have to show that it's an element of the preimage of A intersection the preimage of B. Well, by definition, what's the deal with X? If X is in the preimage of A intersection B, so what is the definition? Let's write it out. the preimage of A intersection B, it's the set of all x in the domain such that what?
F of x is an element of A intersection B.
Yeah. All right, let x be an element of the preimage of A intersection B, therefore by definition, f of x is an element of A intersection B. So f of x is an element of, well, since it's in the intersection of A and B.
A and B.
Yeah. Right? Therefore what? If f of x is in A, so by definition of preimage, we now get that what? X is an element of what? If f of x is an element of A, then x is an element of right? F of x is an element of A. So x is an element of what? Having to do with A. Where's F? And f of x is in A. So x is in what set having to do with A?
The preimage of A.
Preimage of A, yeah. It's in the preimage of A. And, because x is in B, what?
X is the an element of preimage B.
Yeah. Alright, so since it's in both sets, it's in the intersection of the two sets. Right? So we took x in the preimage of A intersection B. Therefore, by definition, f of x is in A intersection B. By the definition of intersection, f of x is in A and f of x is in B. By definition of preimage, x is in the preimage of A and x is in the preimage of B. So that thing that about, images that wasn't true is true with preimages. Like, if f of x was in the image of A, so now here A is in the domain, you couldn't say that x was in A. But with preimages it does work because there's that universal quantification going on. Right? So because f of x is in A, x is in the preimage of A, and because f of x is in B, x is in the preimage of B, so since x is in both these sets, it's in the intersection of the two. So now the other way around, right? Let x be in the preimage of A intersection the preimage of B. Therefore what? What can we do first? What property can we use first? Because x is in the intersection of two sets. What?
X is in the preimage of A and X is in the preimage of B.
Alright, so because x is in the preimage of A, by definition, that makes what?
That's an element of A.
No. X is in the preimage of A. What is in A, though?
F of X.
F of x. I'm sorry, did you say f of x? Maybe your voice cut a little bit there. f of x is in A, and, well, because x is in the preimage of B, where else is f of x?
And B.
Yeah. All right, so f of x is in A and f of x is in B, so f of x is actually in what?
A intersection B.
A intersection B. So, f of x is in A intersection B, so x is in x is where? F of x is in A intersection B, so x is in
The domain.
x is in the domain, but what part of the domain having to do with A intersection B?
Is it the preimage of A intersection B?
Right, exactly. Yep, there it is. So yeah, this preimage thing, it works. It's just, it's got more sort of well-behaved properties than image does. All right. Oh, it's 1:15. All right. So go over these proofs, please. Read the definitions. Go over these proofs. And here's the for next time thing. So take a look at that. And we'll work. We'll go over that problem there. Okay. All right. So have a good weekend, everybody. And I'll check your email. I should have the exam graded for you this weekend, hopefully. Okay. All right.